Hello everyone, and thanks for watching Edupedia World Videos. This video is an introduction to the topic of electric potential energy and electric potential. So we've seen gravitational forces and the analog electric forces, gravitational field and the analog electric field, and we have seen gravitational potential energy, and we'll see the analog of that, which is electric potential energy. Now the electric potential energy is defined at least between two charges. Just like an electric force is defined at least between two charges. Now later on we'll move on to a new concept called electric potential, which will be basically the potential energy configuration created by a single charge, and it will be independent of what the second charge is. Right. So right now the electric potential energy, or rather the change in electric potential energy, because remember potential energy we can take 0 to be anywhere, we always talk about the change in potential energy. So change in potential energy is defined as the negative of the work done by electric forces. Similar to gravitational potential energy, the change in that was the negative of the work done by gravitational forces. So let's say we keep Q1 stationary and we move Q2 to another point such that initially the distance is R1 and finally the distance is R2. Then the force at any point will be repulsive, it will be towards the right, assuming Q1 and Q2 are positive, otherwise their sign will take care of that. So it will be K Q1 Q2 by R squared, and let's say during this time they move a displacement dr. So this will be F dr, which will be the small amount of work done by the force. Remember Q1 is stationary, so no work is done on that. Q2 is moving away due to the electric force, electric repulsive force, which is being applied on it. So F dr, that is K Q1 Q2 by R squared dr, will be the small amount of work done in moving a distance dr. If we integrate it from R1 to R2, we'll get the total work done by the electric forces in moving from R1 to R2. So if we calculate this, this will be R to the power minus 2, whose integral will be R to the power minus 1 by minus 1. So we'll get K Q1 Q2 1 by R1 minus 1 by R2. This is the work done by the electric forces. So the change in potential energy will be the negative of that. So the change in potential energy delta U will be K Q1 Q2 1 by R2 minus 1 by R1. Right, and since potential energy depends on the configuration, in other words the distance between the two, delta U can actually be written as U R2 minus U R1. U R2 is the potential energy when they are at a distance R2 apart, and U R1 is the potential energy when they are at a distance R1 apart. The change in potential energy, remember, will be the final minus initial. Initially it was R1, finally it was R2. So U R2 minus U R1 is equal to this particular quantity. Now often what we'll do is, just like in the case of gravitational potential energy, we'll take a standard reference point to have the potential energy 0. So we'll take an R1 such that U of R1 is 0. What that will give us is U of R2 is equal to K Q1 Q2 1 by R2 minus 1 by R1. Right, so it simplifies it a little bit. We've gotten rid of the second R1 term. Now we can do another thing. We can make this particular choice of R1 where the potential is 0 a very special point, such that this is simplified even further. And again, this is the same thing we did in gravitation. We'll take R1 to be infinity. That means we'll assume that the potential energy is 0 when they are very far apart, when the distance between them is infinite. Now if R1 is infinite, a very nice thing happens. 1 by R1 becomes 0, and so this whole term becomes negligible. Right, so from that we can get the main result of this section, that is U. Now instead of R2 I'll just use R. So U of R is equal to K Q1 Q2 by R. Right, I'll write this again on a new page. Sorry. UR, that is the potential energy between two charged particles of charges Q1 and Q2 when they are at a distance r apart. UR is K Q1 Q2 by R. Now remember, this is not always true. This is only true if IFF. IFF is a short form for if and only if. So UR is this: if and only if we have chosen U is equal to 0 at R is equal to infinity. If at infinity we have chosen U is equal to 5, then at every place U will increase by 5, and this will be K Q1 Q2 by R plus 5. Right, but we've chosen U at infinity to be 0. That is our choice to simplify the formulas. When we see another thing, if Q1 and Q2 are both positive or both negative, U is positive. Right, if U is positive, it's an unstable system. Right, and we can tell that because there will be repulsive forces acting. Right. However, if one of these is positive and the other one is negative, then there will be attractive forces acting. That means this will be a bound system, just like in the case of gravitational forces. When you have bound systems, the potential energy is negative. So when you have a positive and a negative charge together, the potential energy is negative, and their tendency is to make it go towards 0. So their tendency is to move towards each other even further. Right. Now let's move on to the second concept. After potential energy, we'd like to see what electric potential is. Now a useful relation which I'd like to give you to remember the conceptual meanings of this is simply force is to field is proportional to potential energy is to potential. What is force? Force was between two charges, right? Electric field was just for one charge. So that we'll talk about this one charge, and then whenever we introduce the second charge, we'll take care of that at the end by using the formula that force is equal to Q times the electric field. Similarly, potential energy is between two charges. So let's say we have a big configuration of charges and we have another positive charge here whose behavior we want to study. So either we can calculate the potential energy between these two and between these two and between these two and between these two and calculate all of them and add them up. In some cases it will be slightly easier than the electric field one or the forces one because potential energy and potential are scalars, but still it will be quite complicated to handle individually. Instead what we can do is we can actually calculate what is called the potential of this configuration, and if that potential at a particular point has a value 3 units, then according to the charge that has been put, we can calculate the potential energy between that charge and this particular configuration. Because we see that if we want the potential energy between Q2 and something, then it is proportional to Q2, and that remaining thing is called the potential. Right. So again, field was defined for one particular charge so that we can take care of the second charge whenever we need to. Potential is defined for one particular charge or a configuration of charges so that we can take care of the second charge whenever we need to. Right. So I'll write on the proper standard definitions. V is the symbol that is used for potential, right? And V of R, that is the potential at a distance R, can be written as V of R minus V of ref. Ref is the reference point. The reference point is the point where we've chosen the potential to be 0. Now since V is the work done in bringing a charge, a unit charge from infinity to that point, the actual potential energy will be proportional to the charge. So V will actually be U divided by Q. So this can actually be written as U of R minus U of ref divided by Q. Right. Now if we've taken the reference to be infinity, that means U of reference is 0, and from that we get the standard result V of R is equal to U of R by Q. Again, this result is also only true if the reference is chosen to be at infinity. Right. So I'll write down the proper definition as well for you so that you know it. Potential is defined, potential at R is the change in potential energy per unit charge when it's moved from the reference to R. We know that the change in potential will be proportional to the charge of our test charge. If we double the charge of our test charge, then the potential will double, right? Potential energy will double. So potential is defined per unit charge, right? Now let's look at the relationships between potential and electric field as well, right? So we know that U of R2 minus U of R1 is equal to the negative of the integral of R1 to R2 F dot dr, right? The change in potential energy is the negative of the work done by electric forces. Similarly, the change in potential is just this divided by the charge. And what is force divided by the charge? It is the electric field, obviously. We see that the relation is again similar. So this is equal to minus integral of R1 to R2 E, these should be vectors actually, E dot dr, right? Now when we talk about R1 as a reference point or infinity, then we can say V of R2 now I'll write as R, is minus integral of infinity to R E dot dr. So again we see another sort of definition of potential. It is the work done in bringing a unit charge from infinity to a reference point. If the potential at a point is positive, then the work done is positive. That means the charge does not want to go there. If the potential is negative, that means the charge will readily go there, and we need to do negative work to make sure it reaches there slowly. From this we can derive the opposite results as well. If just differentiating this, we can get dV is equal to E dot dr. E dot dr is what? It is Ex dx I cap, or not I cap, we have dot product now, plus Ey dy plus Ez dz. From this we get the inverse relation that gives us the electric field from the potential. Ex is equal to minus del V by del x, and the others are similar. Ey is equal to minus del V by del y, and Ez is equal to minus del V by del z. So if you have a question, for example, in which the potential is given as x cube I cap plus 3xy j cap, then you can calculate the electric field and such easily. So I'm sorry, x cube plus 3xy, potential is a scalar. So the electric field Ex will be minus del V by del x, that is 3x square plus 3y, and similarly Ey will be 3x. So the electric field will be 3x square plus 3y I cap plus 3x j cap, right? So this result gives us the potential from the electric field, and these three results give us the electric field from the potential. Potential is a scalar and electric field is a vector. Finally, we have a concept of equipotential surfaces, and they are just surfaces, as the name suggests, on which a potential is constant. So for example, we'll see use for them later on, but right now let's just take a simple case of a point charge q, right? The potential at a distance r away from it is kq by r. Now q is a constant, k is a constant. That means if r is a constant, then kq by r is a constant. That means a spherical shell of radius r is an equipotential surface. If we draw a spherical shell of radius r, every point here will actually have the same potential. If we draw another equipotential cell of a different radius, this point will not have the same potential at this point, but every point on this equipotential surface will have the same potential. Now obviously two equipotential surfaces cannot intersect, and the perpendicular to the equipotential surface gives us the direction of electric field, because electric field is the direction of change in potential, and we know that in the tangential direction the potential is not changing at all, in fact. So the electric field has to be in the radial direction, which we know from a single point charge as well, that electric field is in the radially outward direction. Right. This completes electric potential. Now we've got our basic main ammunition ready to study some advanced concepts, which we'll do in the next videos. We've learned about electric forces between two charges, which we studied in the form of electric field by a charge or a configuration of charges. We've learned how to calculate problems involving electric potential energy and the electric potential due to a configuration of charges. Thank you.